we will see Class 2, the Mezcal spectroscope at the National Astronomical Observatory of San Pedro Marantil. Mezcal with Z or with S for those who are not Mexican. It should be clarified that Mezcal with Z is a typical spirit drink from certain parts of our country. And it was fascinating to utilize the term in the game. It was intriguing to observe how the words were employed, specifically to refer to the Manchester Echelle spectrometer, located in Baja California. That is, for the Echelle spectrometer of Manchester in Baja California. That's why it's called Mezcal, first with an S, and later, because of the use of the term, it ended up being used as Mezcal with a Z. However, it is a name in some way to ensure that we do not lose the sense of humor within our work. What is Mezcal? Mezcal is an Echelle spectrograph that was designed by Professor John Meeburn specifically for the purpose of studying extended sources in very short wavelength intervals in order to perform long-slit spectroscopy. It was designed to be used in the Anglo-Australian telescope, where its first version was from 1984 to 2001. As you can see, the body, the right part, is the one that is screwed, placed on the plate of a telescope, and what would be the body, the spectrograph, extends to one side. A subsequent version of the instrument, with the same structure and design, was installed in both the Isaac Newton telescope, with a diameter of 2.5 meters, in 1986, and the William Herschel telescope, a 4.2-meter telescope, in 1987. This is the observatory that the boys on the island of La Palma in the Canary Islands. Later, since 1995, Professor Meeburn and his group from the University of Manchester brought the spectroscope to the National Astronomical Observatory, where, already being here, the spectroscope has received improvements both in the electronic part and in the mechanical part, where the academic technicians of our observatory have intervened. In which telescope is this spectrometer used? It is used in the 2-meter telescope, and we can see, in the image on the left, the 2-meter telescope at the National Atomic Observatory. And in the next photograph is the telescope itself, the body of the telescope, that yellow body. And you have the opportunity to witness a small edge of a gray disk, which essentially represents the edge of our 2-meter telescope. In the photo on the left, we have the original appearance of the Mezcal spectrometer as depicted in this photograph. There was obviously a problem in that architecture that was successfully solved with a rebalancing of the telescope, that is, adjusting the mass distribution to one side of the instrument. So, in order to avoid guiding problems, the telescope must be rebalanced, and then the weights are distributed in such a way that the moments of inertia allow us to guide the telescope calmly and without forcing the motors too much. However, if someone wished to change the angle of position of the slit, they had to rotate the stage in order to achieve this adjustment. And when the plate rotates, the distribution of weight changes, and the telescope would need to be rebalanced again. For that reason, in the year 2003, it was thought to put a counterweight on it. And it is the photograph that you see in the central part. There we see how a structure was put in place in which the weights were added and effectively calculated in such a way that the plate can rotate freely, and that does not alter the distribution of the weights. So that already facilitated us to move in a more convenient manner. Without the necessity of making new balances, it provided us with the opportunity to modify the angle of position of our observations. So, with all of these characteristics, the weight of the Mezcal spectrometer is approximately around 320 kilograms in total. Optical design of the spectrograph. So there are two doubles that focus both the light coming from the telescope, the grating, and the light that, after being scattered, goes to the detector. Before IPCS were used, now a CCD is used. The diameter of the lens is about 10 centimeters and the focal length is 80 centimeters. The angle of separation between the input and output optical axis is at least 3.3 degrees, and this is because the diffraction grating is a grating with an exceedingly large angle, as we saw it at the beginning of our observation. So that's practically the reflection deviates very little, and that allows us to have this experimental arrangement that uses this length precisely to be able to do it with a long slit. The grating has a high blaze angle of 63 degrees with 26 min and a ruling of 31.6 lines per mm over an area of 128 x 254 mm. There you can see initially the diagram illustrating what blaze's angle would be. And in the photograph, that is precisely a photo depicting the structure where the diffraction grating is located and can be observed clearly and distinctly. She is standing, as you can see, in a system that is precisely positioned where it is taken with the hands in order to place it in the spectroscope. Mezcal has two modes of observation. In addition to the direct image is when we don't put anything, and we see the image as it is without going through any slit or grid. A mirror is set and we view the image as it arrives at the telescope. However, aside from that, the image has all the modes for spectroscopy. The long slit mode. Yes, it is about a slit of maximum 30 millimeters, which corresponds approximately to 6.5 minutes. It is larger than the CCD field, with three possible widths. They are 170, 150, and 300 microns, which are approximately equivalent to 1, 2, and 4 arc seconds. And that would take us to 6, 13, and 26 kilometers per second respectively. That with the original slit, with the original 24 millimeter CCD. Well, the other one is referred to as anti-slits, where you have plates with small slits, 5 small slits, along with an additional one, in the case of the 150 microns ones, spaced 3 millimeters apart from each other. So it's like taking many spectra at the same time, many slits. That is advantageous when we have dependable sources that we can examine multiple at once simultaneously. For gaseous nebulae, the long slit is much more convenient in the case of we can rotate in the same position. That is because of the counterweight I mentioned. Now you can make this movement without rebalancing our telescope again. This spectral analysis was created by Boss and Gibbon because his primary interest was in studying planetary nebulae. What are the most important clouds in planetary nebulae? H alpha, nitrogen 2, oxygen 3, sulfur. So, he designed it in a way that in the same or very close to a certain angle to position his diffraction grating, those spectral lines of different orders would be found in that field, ensuring the alignment of the grating with the desired angle for observing the spectral lines of different orders. So, for example, we have important lines from order 87, order 114, order 85. All the lines are there, which are from different orders. However, if we apply a filter to the input, then the color red will remain red, and the diffractions that the red will experience are solely those of the red color. So, that allows us that with a filter, for example, the one we call the H-alpha filter, only the H-alpha lines and the 2 nitrogen lines that accompany it, which are 6548 and 6583, can be observed. By using a redder filter like sulfur, only lines 6717 and 6731 would be visible. Switching to O3 gives 5.07. These filters possess a width of approximately 90, the red ones, and 60, the oxygen-3 filter. And they allow us to separate from the beginning, before there is dispersion, the red light, the blue light, etc., with which we are going to work. So filters are very important. There are additional fascinating lines that can be observed at that particular location. We see in the diagram that there are oxygen lines 1, sodium lines, calcium lines, which can also help with other types of phenomena, other types of astrophysical processes, not necessarily those that occur in planetary nebulae. So they can be observed with the correct filters. When we acquire a spectrum of the comparison lamp, which is within our control in the spectrometer apparatus, utilized for the purpose of measurement and analysis. We observe, for instance, that in the situation of the lamp suggested by Professor Meibel, it is the thorium-argon one, and it possesses approximately adequate distributed lines to assist us in decreasing the spectra. It has lines both in the H-alpha region and in the Xygeno-3 region, and that's what we're seeing here in these images. How do we acquire the information? We do it through a solid-state detector, a CCD. In the initial jobs we have, we utilize the site brand CCD, where the dimensions are 1000 by 1000, with pixels measuring 24 microns, providing them with specific scales. Subsequently, we were able to utilize one of these Marconi E2B detectors, which has also generated a significant amount of data for our research endeavors. It possesses a smaller pixel, which greatly aids in addressing the configuration issue and achieving a high-quality resolution. And what is needed in this location are temperatures on the order of 100 degrees below zero to meet the requirements. And the one that is currently working in the year 2024 is one from Spectral Instrument called SI2, which is also an E2B, very similar to the Marconi 2000x2000. 13.5 microns with this plate scale of 0.174 seconds per pixel and approximately 0.03 stars per pixel. So there we have a photograph of what an astronomical detector is. It is a chip CCD. These CCDs are also the ones that come in current photographic cameras, but these detectors are specifically designed for scientific operation purposes. Therefore, they do not care so much about being able to handle input colors, but rather prioritize being sensitive to the majority of detectors and also having the capability to determine the range of brightness with high sensitivity. So it is more important than capturing a visually stunning photograph like professional cameras do with their high-quality CCDs. This is one more function that you have in your repertoire. Good. Another very interesting thing is the whole system. Once the spectroscope has all its lenses, it has its CCD, its filters, etc. How much light do we lose? And that is very interesting. Here we have a table that shows us the total efficiency at each wavelength, whether in resolved sources, as in the case of nebulae, or in point sources, as in the case of stars. And the efficiency is actually extremely low. We are specifically referring to the case of the maximum total efficiency, and we are talking about a value of around 13%. So, it means that a significant amount of light is lost. Remember that the dispersion of light is the entirety of what is visible. It scatters, and we are currently capturing a very small fragment of that scattered light. So, that is the reason why in the end, the efficiency we have is really low, and we need to observe more in order to reach the weakest areas and be able to conduct the studies we require. I believe we're going to take another brief pause and catch up with each other at a later time.